Hello there, and welcome to Nick's Documentaries, where the darkness gives way to depths we can barely fathom, and where silence speaks in currents older than continents. Tonight, we're not climbing mountains or crossing deserts. We're descending down into the blue, into the cold, into the vast liquid realm that covers more than 2/3 of our planet's surface, yet remains more mysterious to us than the surface of the moon. This is the story of the ocean. Not the ocean as a backdrop for adventure stories, or a source of seafood, or a highway for ships, but the ocean as it actually is. Ancient, powerful, indifferent to human concerns, yet intimately connected to every breath we take, every raindrop that falls, every degree of temperature that shapes our climate. Before we begin this descent into deep time and deeper waters, I'd love to know where in the world you're listening from tonight, and whether you can hear the ocean from where you are. There's something profound about the fact that no matter where you stand on Earth, you're never more than a few thousand kilometers from the sea. The ocean surrounds us, defines us, shaped the evolution of life itself, and continues to regulate the very conditions that make our existence possible. If this kind of deep exploration draws you in, if you find yourself staring at waves and wondering what lies beneath, what came before, what patterns connect the smallest plankton to the largest currents, I'd be grateful if you tapped like or subscribed. It helps this quiet signal find others who look at water and see not just a surface, but a history, a mystery, a world within our world that we're only beginning to understand. And so settle in, let the world around you grow quiet, and prepare to sink beneath the surface, to watch as the light fades and the pressure builds, to trace the story of water on Earth from its arrival on a molten planet to the complex, layered, living ocean that exists today. We're going to watch the ocean form, watch it freeze and thaw, watch life emerge from its depths, and watch that life transform the water itself. We're going to see how the ocean breathes, how it remembers, how it connects everything to everything else in ways we're still discovering. The ocean has a memory longer than stone. It has witnessed everything. And tonight, in the darkness, we're going to listen to what it has to say. In the beginning, there was no ocean. Let's go back, not just centuries or millennia, but billions of years. Back to a time when the Earth was young, when the planet was still cooling from its violent birth, when the surface was a hellscape of molten rock and toxic gases and constant bombardment from space. There was no ocean then. There couldn't be. The surface temperature was too high. Any water that existed would have been vapor, part of the thick, choking atmosphere that wrapped the young planet in a greenhouse, so intense that even lead would have been liquid on the surface. But water was there, even then, not as ocean, but as potential. Water molecules, hydrogen and oxygen bound together, existed in the solar system from its formation. Comets, those dirty snowballs of ice and rock, carried vast amounts of water. Asteroids contained it locked in minerals. The very dust that coalesced to form the Earth held water in its chemical structure. As the planet grew, as it swept up more and more material from the swirling disk around the young sun, it accumulated water, but that water couldn't settle. It remained in the atmosphere, part of the choking, steaming envelope that made the early Earth uninhabitable by any standard we'd recognize. Then, slowly, over hundreds of millions of years, the planet cooled. The surface solidified, forming the first thin crust of rock over the churning mantle below. Volcanoes erupted constantly, adding more gases to the atmosphere, more water vapor. But now, with a solid surface, the temperature began to drop. And at some point, perhaps around CD&C billion years ago, perhaps earlier, we're not entirely sure, the temperature dropped below the boiling point of water at the surface pressure. and it began to rain, not a gentle rain, not a passing shower. This was a deluge that may have lasted millions of years. Water vapor condensing out of the atmosphere, falling as rain so heavy and so prolonged that it's difficult for us to even imagine. Rain that filled every depression, every crater, every low point on the surface. Rain that accumulated, pooled, spread, connecting into larger and larger bodies of water. This was the birth of the ocean. Not all at once, but gradually, as the rain continued and the water accumulated and the earliest ocean basins filled. This primordial ocean was not like the ocean we know. It was probably hot, heated from below by the still cooling planet. It was acidic, filled with dissolved gases from the volcanic atmosphere. It was utterly lifeless. A sterile chemical solution under a sky that glowed with volcanic lightning and the dull red of constant eruptions. But it was water, liquid water, and that made all the difference, because water is extraordinary. It's not just another chemical compound. It has properties that make it unlike almost anything else in the universe. It's a solvent, able to dissolve more substances than almost any other liquid. It expands when it freezes, making ice float, a quirk of physics that will later prove crucial for the survival of aquatic life. It has a high heat capacity, meaning it can absorb enormous amounts of energy without changing temperature much, making it a perfect. And most importantly, water provides a medium where complex chemistry can happen, where molecules can move freely, encounter each other, react, combine into larger structures. The origin of life, whenever and however it happened, almost certainly occurred in water. The ocean was life's cradle, its first home, and for billions of years, its only home. The early ocean was shaped by forces we can barely imagine. The Earth's rotation was faster then, spinning perhaps every 5 or 6 hours instead of 24. This meant more frequent day-night cycles, stronger Coriolis forces affecting currents. The moon was closer, much closer, perhaps only Ursaring kilometers away, instead of the Sembibasher kilometers it is today. Its gravitational pull created tides that dwarfed anything we experience now, tides that may have swept hundreds of kilometers inland twice per day. These massive tides stirred the ocean constantly, mixing surface and deep waters, distributing heat and chemicals, creating dynamic environments where complex chemistry could flourish. Some scientists think these tidal pools, alternately flooded and exposed, heated and cooled, may have been the perfect environment for the first self-replicating molecules to evolve. The ocean also interacted with the solid Earth in ways that shaped both. Seawater seeped into cracks in the hot rock of the ocean floor, was heated to extreme temperatures, reacted with the minerals there, and emerged as hydrothermal fluids, rich in dissolved metals and minerals. These hydrothermal vents, which still exist today, may have been the sites where life first emerged, using the chemical energy from the vent fluids instead of sunlight. And gradually, over hundreds of millions of years, the ocean changed. It grew less acidic as the carbon dioxide in the atmosphere dissolved into the water and reacted with rocks, forming carbonates that precipitated out and settled to the bottom. It grew less hot as the planet's interior slowly cooled. It grew more complex chemically as rivers began to flow, carrying dissolved minerals from the weathering of rocks on land. By about Sendian Bat billion years ago, the ocean had reached something like a stable state, still very different from today's ocean, still devoid of free oxygen, still sterile by modern standards, but recognizably an ocean, a vast body of water covering most of the planet's surface, with currents driven by winds and tides and temperature differences, with a seafloor that was already beginning to show the first signs of plate tectonic activity. And somewhere in this ocean, in its depths or in tidal pools or near hydrothermal vents, chemistry became biology. Molecules began to replicate themselves. Natural selection began its slow, patient work. Life emerged. And once life appeared, the ocean would never be the same again, because life doesn't just inhabit the ocean. It transforms it, shapes it, becomes part of the very definition of what the ocean is. Damjin, for the first 2 billion years or so of life's existence, the ocean was a microbial world. Bacteria and archaea, single-celled organisms too small to see without a microscope, filled the water. They clustered around hydrothermal vents, formed mats on the seafloor, floated in the sunlit surface waters. They were simple, but they were alive, and they were changing everything. Some of these early microbes evolved photosynthesis, the ability to use sunlight to convert carbon dioxide and water into sugars and oxygen. At first, this happened without producing oxygen, using different chemical pathways. But around 1 billion years ago, cyanobacteria evolved oxygen-producing photosynthesis, the same basic process that plants use today. This was revolutionary and catastrophic. Because oxygen, which we depend on for every breath, was poison to most of the organisms that had evolved in its absence. The Great Oxidation Event, as it's called, was probably Earth's first mass extinction, wiping out countless species of anaerobic bacteria. But the oxygen didn't accumulate in the atmosphere immediately. First, it had to saturate the ocean, reacting with dissolved iron and other minerals. This created vast deposits of iron oxide, banded iron formations that settled to the ocean floor. You can see these formations today in ancient rocks, alternating layers of iron-rich and iron-poor sediment, each layer representing a pulse of oxygen production, followed by its reaction with dissolved iron. For hundreds of millions of years, the ocean acted as a vast chemical buffer, absorbing the oxygen that photosynthetic organisms produced, preventing it from accumulating in the atmosphere. But eventually, around 1 billion years ago, the ocean was saturated. There was no more dissolved iron to react with, and the oxygen began to build up in the atmosphere. This transformed the ocean in profound ways. Oxygen is reactive. It changes the chemistry of seawater, affecting what minerals can form, what elements stay dissolved, how nutrients cycle. It also opened up new metabolic possibilities for life. Organisms that could use oxygen for respiration gained access to far more energy than anaerobic pathways provided. They could grow larger, move faster, do more. But the ocean remained a microbial world for another billion years or more. Complex multicellular life, the kind we're familiar with, didn't appear until much later. Why the delay? We're not entirely sure. It may have been that oxygen levels needed to rise higher. It may have been that certain evolutionary innovations had to accumulate first. It may have been that the conditions were simply too stable, providing no pressure for organisms to become more complex. Whatever the reason, around Lupecto Bapek million years ago, things began to change. The first multicellular organisms appeared, simple at first, soft-bodied creatures that left few fossils. But then, in a relatively short period, geologically speaking, maybe just sensors million years, life exploded into diversity. Well, this was the Cambrian explosion, and it happened in the ocean. Within this brief window, most of the major animal body plans we know today appeared. Arthropods with jointed legs and segmented bodies, mollusks with shells, echinoderms with five-fold symmetry, chordates, the group that would eventually give rise to vertebrates, to fish, to us. The ocean suddenly became crowded with life in forms both familiar and utterly alien. Trilobites scuttled across the seafloor. Anomalocaris, a meter-long predator with grasping appendages and a circular mouth full of teeth, hunted in the open water. Bizarre creatures like Hallucigenia and Opabenia defied easy classification. Their body plans experiments that worked for a time, but didn't lead to lasting lineages. Why did this happen? What triggered the Cambrian explosion? Again, we're not entirely certain. Rising oxygen levels played a role, allowing larger, more active bodies to evolve. The evolution of hard shells and skeletons provided protection and also created a better fossil record, making the explosion seem more dramatic than it might have been. Predation drove an arms race, prey evolving defenses, predators evolving better tools to overcome those defenses. But there may have been something about the ocean itself, about its chemistry, its circulation, its nutrient distribution that made this moment ripe for innovation. The ocean wasn't just a passive stage where evolution performed. It was an active participant, providing the conditions, the challenges, the opportunities that shaped what life became. From the Cambrian onward, the ocean has been dominated by complex multicellular life. Fish evolved, first jawless, then with jaws that made them more effective predators. They radiated into countless forms, from tiny plankton feeders to massive armored predators like Dunkel osteus, a surmeter fish with jaws that could crush bone. Marine reptiles evolved, moving from land back into the ocean, adapting to aquatic life in ways that made them formidable predators. Ichthyosaurs looked like dolphins but were reptiles, perfectly streamlined for high-speed swimming. Plesiosaurs had long necks and powerful flippers. Mosasaurs were massive, some reaching sterwometers in length, dominating the oceans of the late Cretaceous. And then there were the invertebrates, the creatures without backbones that make up the vast majority of ocean life even today. Cephalopods, relatives of squid and octopus, evolved into hunters of remarkable intelligence. Ancient nautiloids had straight shells several meters long. Ammonites, with their coiled shells, became one of the most successful groups in ocean history, persisting for over 7 million years before finally going extinct with the dinosaurs. And corals built reefs, though not always the same kinds of corals we know today. Different groups evolved the reef-building lifestyle at different times, creating underwater structures that provided habitat for countless other species. Sponges, among the simplest multicellular animals, filtered vast quantities of water, playing crucial roles in nutrient cycling. The ocean became layered not just physically with depth, but ecologically. In the sunlit surface waters, photosynthetic plankton formed the base of the food web, converting sunlight and dissolved nutrients into living matter. Zooplankton grazed on the phytoplankton. Small fish ate the zooplankton. Larger fish ate the small fish. At the top of the food web sat the apex predators, the largest, fastest, most powerful hunters. But below the sunlit zone, in the twilight depths and the abyssal darkness, other ecosystems developed. Here, where no sunlight penetrated, life depended on the rain of organic matter from above, the constant snow of dead plankton, and fecal pellets and other detritus drifting down from the surface. Scavengers and filter feeders made their living from this marine snow. And where it accumulated on the seafloor, burrowing creatures stirred the sediment, mixing nutrients, creating habitats, and at the very deepest parts, at hydrothermal vents and cold seeps, ecosystems developed that didn't depend on sunlight at all. Here, chemosynthetic bacteria formed the base of the food web, using chemical energy from the vents to produce organic matter. Tube worms, clams, crabs, and other creatures clustered around these oases of life in the deep darkness, entire communities that existed in complete independence from the surface world. The ocean, you see, is not one place. It's many places, many environments, each with its own conditions, its own challenges, its own forms of life adapted to survive there. From the freezing polar seas to the warm tropics, from the sunlit surface to the crushing pressures of the deepest trenches, the ocean contains multitudes, and life has filled every niche, every possible environment, adapting and diversifying over hundreds of millions of years into the staggering biodiversity we see today, or saw. Because we're losing it faster than we realize, the ocean breathes. Not literally, of course. It doesn't have lungs, but it exchanges gases with the atmosphere, absorbs oxygen, releases carbon dioxide, in rhythms that span days and seasons and decades. This breathing is fundamental to how the ocean works, to how life in the ocean survives, to how the ocean regulates Earth's climate. Near the surface, where sunlight penetrates, photosynthesis by phytoplankton produces oxygen. These microscopic organisms, mostly single-celled algae and cyanobacteria, are the ocean's primary producers. They're also the primary producers for the entire planet. It's estimated that phytoplankton produce about half of the oxygen in Earth's atmosphere. Every other breath you take comes from the ocean. Think about that for a moment. Half of the oxygen that keeps you alive is produced by organisms you can't even see, floating in water, using sunlight and dissolved nutrients to grow and reproduce. The ocean isn't just a source of food or a highway for shipping. It's a life support system, actively maintaining the atmospheric composition that makes land-based life possible. But oxygen doesn't stay at the surface. Ocean currents mix the water, carrying oxygen-rich surface water down into the depths. This mixing is crucial. Without it, the deep ocean would be anoxic, devoid of oxygen, unable to support most forms of life. Fish, squid, whales, all the large mobile animals we associate with the ocean depend on dissolved oxygen to breathe through their gills, or, in the case of whales, to replenish the oxygen they hold in their blood and muscles between dives. The myth happens through wind stirs the surface, creating turbulence that pulls deeper water upward and pushes surface water down. Waves, especially storm-driven waves, can mix water to considerable depths, but the most powerful mixing comes from a process called thermohaline circulation, the ocean's great conveyor belt. This circulation is driven by differences in temperature and salinity. In the polar regions, especially the North Atlantic and around Antarctica, surface water becomes very cold and very salty. The cold makes it dense, the saltiness makes it even denser, and this dense water sinks, plunging down into the deep ocean, carrying with it the oxygen it absorbed at the surface. This sinking water flows along the bottom, spreading throughout the deep ocean basins, creeping across the abyssal plains at a pace so slow it's measured in centimeters per second. But over decades and centuries, this water travels vast distances, from the North Atlantic all the way to the Pacific, a journey that can take 1,000 years or more. Eventually, in other parts of the ocean, this deep water rises back to the surface, a process called upwelling. It brings with it nutrients from the deep, fertilizing the surface waters, supporting massive blooms of phytoplankton. The most productive fishing grounds in the world are often in upwelling zones, where this deep, nutrient-rich water reaches the surface and sparks explosive growth of marine life. But this conveyor belt does more than circulate nutrients. It circulates heat. Warm water from the tropics flows toward the poles at the surface, releasing heat to the atmosphere, moderating polar climates. Cold water from the poles flows toward the equator in the deep ocean, absorbing heat as it eventually rises and returns to the surface. This circulation distributes solar energy around the planet, reducing temperature extremes, making Earth more habitable, and it circulates carbon. The ocean is a vast carbon reservoir, holding far more carbon than the atmosphere. Some of this carbon is dissolved as carbon dioxide. Some is incorporated into the shells of marine organisms, calcium carbonate structures that eventually sink to the seafloor when the organisms die. Some is organic carbon, the bodies and wastes of marine life. The ocean absorbs about a quarter of the carbon dioxide that human activities release into the atmosphere each year. This is both a blessing and a curse. It's a blessing because it slows the accumulation of company in the atmosphere, reducing the rate of global warming. It's a curse because the absorbed company reacts with seawater to form carbonic acid, lowering the ocean's pH in a process called ocean acidification. This acidification is already having effects. It makes it harder for organisms to build shells and skeletons from calcium carbonate. Corals, shellfish, some types of plankton all struggle in more acidic water, and since many of these organisms are foundational to ocean food webs, the impacts could cascade through entire ecosystems. The ocean's breathing, its gas exchange with the atmosphere, is also affected by temperature. Warm water holds less dissolved gas than cold water. As the ocean warms due to climate change, it becomes less able to absorb oxygen from the atmosphere. Combine this with increased stratification, warmer surface water sitting on top of colder deep water with less mixing between them, and you get expanding zones of low oxygen, dead zones where marine life suffocates. We're already seeing this. In some parts of the ocean, oxygen levels have dropped by over 500 R in the past years. Doesn't sound like much, but for organisms already living near their oxygen tolerance limits, it's the difference between survival and death, and the zones are expanding both in size and in number. The ocean's breath is becoming more labored, and this should terrify us. Because if the ocean can't breathe properly, if the circulation that oxygenates the deep ocean slows or stops, if warming and acidification continue, then the ocean's ability to support life diminishes. And since we depend on the ocean for oxygen, for climate regulation, for food, the ocean's struggles become our struggles. We are not separate from the ocean. We never have been. We evolved in a world shaped by the ocean's chemistry. We breathe the oxygen it produces. We eat the fish it sustains. We live under a climate it moderates. When we change the ocean, we change the conditions of our own existence. The ocean remembers. In its depths, in the layers of sediment on its floor, in the chemistry of its water, it records everything. And temperature changes, atmospheric composition, the rise and fall of species. The ocean is a vast archive, and we're writing a new chapter in its history. Whether that chapter ends with recovery or collapse depends on choices we're making right now. And let's go to the poles, to the ends of the earth where the ocean meets ice, where water transforms into a solid landscape, where life persists despite conditions that seem utterly inhospitable. The polar oceans, the Arctic and the Southern Ocean around Antarctica, are among the most extreme environments on the planet. And they're among the most important. The Arctic Ocean is unique. It's the smallest ocean, almost landlocked, surrounded by continents and connected to the Atlantic and Pacific by narrow straits. For much of the year, its surface is covered by sea ice, frozen seawater that forms during the long polar night and partially melts during the brief summer. This sea ice is not just frozen water. It's an ecosystem, a habitat, a crucial part of how the Arctic Ocean functions. The underside of the ice is colonized by algae, single-celled plants that grow in the dim light that penetrates the ice, forming thick mats that provide food for zooplankton. The zooplankton, in turn, feed fish, which feed seals and whales and seabirds, supporting an entire food web based on the productivity of ice bottom algae. The ice itself provides hunting platforms for polar bears, haul-out sites for seals, breeding grounds for some seal species that give birth on the ice. Without sea ice, these species couldn't exist. They're adapted to a frozen ocean, dependent on the ice in ways that make it impossible for them to simply move elsewhere if the ice disappears. And it is disappearing. Arctic sea ice has declined dramatically over the past few decades. The summer minimum extent, the smallest area covered by ice each year, has shrunk by about 500 centimeters since satellite measurements began in the late Ichenjubai-Chirishers. The ice is also thinner, younger, more fragile. Old, thick, multi-year ice that used to persist for decades is being replaced by thin, seasonal ice that forms each winter and melts each summer. The consequences of this ice loss ripple outward. Less ice means less reflection of sunlight back into space. Ice is white, highly reflective. Open ocean water is dark, absorbent. As ice melts, more solar energy is absorbed, warming the ocean, which melts more ice, in a feedback loop that accelerates the warming. Okay. Less ice also means changes in ocean circulation. The formation of sea ice is a crucial part of how deep water forms in the Arctic. When seawater freezes, most of the salt is excluded from the ice, making the surrounding water saltier and denser. This dense water sinks, driving circulation. If less ice forms, less dense water is created, and the circulation weakens. The Southern Ocean surrounding Antarctica is different. It's not landlocked, but open, with no barriers to prevent currents from flowing all the way around the continent. The Antarctic Circumpolar Current, the world's largest ocean current, flows eastward around Antarctica, connecting the Atlantic, Pacific, and Indian Oceans, mixing their waters, playing a crucial role in global ocean circulation and climate. Antarctica itself is a continent covered by a massive ice sheet, ice that's formed from snowfall on land, not from frozen water. This ice sheet contains about 500 tiers of Earth's fresh water. If it all melted, global sea levels would rise by about Luxusmeters. That's not going to happen quickly, but even partial melting could raise sea levels by several meters, enough to inundate coastal cities worldwide. The Southern Ocean is also incredibly productive in some areas. Upwelling brings nutrients from the deep, supporting massive blooms of phytoplankton, which support krill, small shrimp-like crustaceans that exist in vast swarms. Krill are the foundation of the Antarctic food web. Eaten by fish, squid, seals, penguins, and the largest animals ever to exist, baleen whales. Blue whales, fin whales, humpback whales, all feed primarily on krill. These giants migrate to Antarctic waters during the summer to gorge on the krill swarms, building up fat reserves that will sustain them during their migration to warmer waters to breed. The abundance of krill in the Southern Ocean is what allows these enormous animals to exist. But krill populations are declining. Warming waters, changing ice conditions, acidification, all affect krill. And krill fishing, driven by demand for omega-6 supplements and aquaculture feed, is extracting millions of tons of krill each year. If krill populations collapse, the entire Antarctic ecosystem could follow. Both polar oceans are changing faster than almost anywhere else on Earth. The Arctic is warming at more than twice the global average rate. Antarctica is showing signs of accelerating ice loss, particularly in West Antarctica, where warm ocean water is undermining ice shelves from below, causing them to thin and break apart. These changes aren't just local. They affect the entire planet. Melting ice adds fresh water to the ocean, affecting salinity and density, potentially altering the thermohaline circulation that regulates global climate. Changes in polar ocean productivity affect carbon cycling, nutrient distribution, fish stocks far from the poles. The frozen ocean is thawing, and we don't fully understand what that means, what tipping points might be crossed, what feedback loops might be triggered, what the new equilibrium will look like. We're conducting an uncontrolled experiment on a planetary scale, and the polar oceans are where the effects are most visible, most dramatic, most terrifying. Standing on sea ice, feeling it flex beneath your feet with the swell of the ocean below, you're acutely aware of how thin the barrier is between water and ice, between liquid and solid, between one kind of world and another. Barrier is melting. And on the other side is an ocean we don't recognize, an Arctic without summer ice, an Antarctic with accelerating ice loss, a world we've never seen, a world we're creating without knowing if we'll survive in it. Now let's descend, down past the sunlit surface waters, down through the twilight zone where the last rays of light fade to nothing, down into the eternal darkness of the deep ocean. This is the largest habitat on Earth. The abyssal plains and ocean trenches that cover more than half the planet's surface, and it's the least known, less explored than the surface of Mars. The deep ocean begins where sunlight ends, around Urbeck meters depth. Below this, photosynthesis is impossible. There's not enough light. The world becomes fundamentally different, alien in ways that make it difficult to imagine without experiencing it. The pressure increases by 1 atmosphere, about kilograms per square centimeter, for every meters of depth. At meters, the pressure is EBAT times atmospheric pressure. At the deepest point in the ocean, the Challenger Deep in the Mariana Trench, nearly meters down, the pressure is over atmospheres, more than batons per square inch. It would crush a human instantly. Submarines require thick steel hulls to withstand it. The temperature drops. In most of the ocean, below the surface layer that's warmed by the sun, the temperature is between and 6 degrees Celsius. Degrees Celsius. In some deep trenches, it's just above freezing. The water is intensely cold, dark, and pressurized beyond anything we experience on land, and yet, life exists here. The deep ocean is not a barren wasteland. It's teeming with life, though in forms adapted to conditions we can barely comprehend. In the mesopelagic zone, the twilight zone between Urbicand meters, there's still a tiny amount of light filtering down from above, enough for some animals to see, though not enough for plants. This is the realm of bioluminescence, where many organisms produce their own light through chemical reactions. Lanternfish, squid, jellyfish, even bacteria flash and glow in the darkness, using light for communication, for attracting prey, for confusing predators. Some of these organisms migrate vertically each day, the largest migration of animals on Earth. They spend the day in the deep, where it's dark and safe from predators. At night, they rise to the surface waters to feed on plankton, then descend again before dawn. Billions of tons of biomass moving up and down through the water column every 6 hours, a daily rhythm that's gone on for millions of years. Below the twilight zone is the bathypelagic, the midnight zone, from to meters. Here, there's no light at all. Animals are blind or have developed enormous eyes to catch the faintest bioluminescent glow. Food is scarce. Most organisms here are either predators, hunting the sparse prey, or scavengers, waiting for organic matter to drift down from above. The adaptations here are remarkable and sometimes grotesque. Anglerfish have evolved a bioluminescent lure dangling in front of their mouths, attracting prey in the darkness. Some species have jaws that can unhinge to swallow prey larger than themselves. Because when you encounter food in the deep, you can't afford to be picky about size. Gulper eels have enormous mouths and extendable stomachs. Viperfish have teeth so large they can't close their mouths. And then there's the abyssal zone, Su, Ling 2, low limmators, and below that, the Hattel zone, the deepest trenches down to nearly Shir-E limmators. These are the most extreme environments in the ocean. The pressure is crushing, the cold is intense. The darkness is absolute, food is incredibly scarce. And yet, when scientists have descended to these depths in submersibles or sent down cameras, they've found life. Fish, shrimp, amphipods, sea cucumbers, anemones, bacteria, not in great abundance, but present, surviving, adapted. How do they survive? Many are scavengers, feeding on the carcasses of whales and large fish that sink to the bottom, rare but concentrated sources of food. When a whale dies and sinks to the ocean floor, it creates an oasis, a whale fall that supports a specialized community of scavengers and decomposers for decades. Hagfish, sleeper sharks, crabs, worms all feed on the carcass, extracting every bit of nutrition to them. But perhaps the most remarkable ecosystems in the deep are those that don't depend on food from above at all. Hydrothermal vents, discovered only in the Ichen Julbite Tiras, are places where seawater seeps into cracks in the ocean floor, is heated by magma below, and erupts back out as superheated fluid, sometimes exceeding Seabide degrees Celsius. These fluids are rich in dissolved minerals and chemicals, sulfides, methane, hydrogen, and bacteria have evolved to use these chemicals as an energy source, chemosynthesis instead of photosynthesis. These bacteria form the base of a food web that includes giant tube worms, some over meters long, clams, mussels, crabs, shrimp, fish, all thriving in conditions that would kill most surface organisms. The tube worms are particularly fascinating. They have no mouth, no digestive system. They're filled with chemosynthetic bacteria that live in their tissues in a symbiotic relationship. The worm provides the bacteria with hydrogen sulfide from the vent fluids. The bacteria provide the worm with nutrients. It's a partnership that allows life to exist in one of the most hostile environments on Earth. These vent communities exist in complete independence from the sun. Even if the sun went out, even if the surface ocean froze solid, these ecosystems could persist, powered by the Earth's internal heat. They give us a glimpse of what life might look like on other worlds, on the moons of Jupiter or Saturn, where liquid water might exist beneath ice, where similar chemosynthetic ecosystems might thrive around hydrothermal vents. The deep ocean also plays crucial roles in global cycles, roles we're only beginning to understand. The rain of organic matter from the surface, the marine snow, transports carbon from the atmosphere to the deep ocean, where it can be sequestered for centuries or millennia. This biological carbon pump is one of the major mechanisms by which the ocean absorbs carbon dioxide from the atmosphere. But it's fragile. Changes in surface productivity, in the types of plankton that dominate, in ocean chemistry, all affect how much carbon is transported to the deep and how long it stays there. We're altering these processes in ways we don't fully understand, with consequences that could be profound. The deep ocean is also a repository of mineral resources. Manganese nodules, potato-sized lumps of metal oxides, litter the abyssal plains in some areas. Hydrothermal vents deposit concentrated ores of copper, zinc, gold, and other valuable metals. There's growing interest in deep-sea mining, extracting these resources from international waters. But we know so little about the deep ocean. The ecosystems there are poorly studied, poorly understood. We don't know how resilient they are, how quickly they could recover from disturbance, What species exist that we haven't yet discovered? Mining the deep ocean could destroy unique ecosystems before we even know they exist. The deep is not empty space. It's not a waste dump. It's home to communities of life that have evolved over millions of years to thrive in conditions we find almost unimaginable. And it plays roles in global processes, climate regulation, carbon cycling, that make it essential to the functioning of the planet as a whole. When we talk about protecting the ocean, we can't just focus on the surface, on the colorful reefs and the charismatic megafauna. We have to think about the entire water column, from surface to seafloor, from the sunlit shallows to the crushing depths of the trenches. The ocean is one interconnected system, and what happens in the deep affects the surface, and what happens at the surface affects the deep. The deep ocean is the largest biome on Earth, and we're only beginning to understand it. In the darkness, in the cold, in the pressure that would kill us instantly, life persists. Adapted, specialized, strange, beautiful in its alienness. The deep holds secrets we haven't yet discovered, species we've never seen, processes we don't understand. And it's worth protecting not just for what we might gain from it, but for its own sake, for the simple fact that it exists, that life has found a way to flourish even there. And for most of human history, the ocean was a mystery, a barrier, something to be feared and respected. Early sailors hugged the coastlines, venturing into open water only when necessary, navigating by the stars and the patterns of waves, passing down knowledge of currents and weather through stories and songs. But humans have always been drawn to the sea. Coastal peoples developed cultures intimately connected to the ocean's rhythms, timing their lives to the tides, to the migrations of fish, to the seasonal patterns of storms and calm. They learned which fish were safe to eat and which weren't, where to find shellfish, how to read the water for signs of danger or abundance. The ocean provided food, of course. Fish, shellfish, seaweed, marine mammals. Coastal populations could support larger populations than inland ones because the ocean was a reliable source of protein and nutrients. Some cultures developed sophisticated fishing techniques using traps, nets, hooks, poisons derived from plants. They learned to preserve fish through drying, smoking, salting, fermenting, but the ocean was also a highway. Once humans developed boats capable of open water travel, the ocean connected distant lands rather than separating them. Polynesians crossed thousands of kilometers of open Pacific, navigating by stars and swells and the flight patterns of seabirds, settling islands from Hawaii to New Zealand to Easter Island. Phoenicians sailed the Mediterranean and beyond, establishing trade networks that connected cultures and spread ideas. Vikings crossed the North Atlantic, reaching Greenland and North America centuries before Columbus. These ocean voyages required courage and skill and intimate knowledge of the sea. Sailors learned to read the ocean, to interpret the color of the water, the behavior of clouds, the feel of the wind. They developed technologies, better sails, better hulls, navigational instruments like the compass and the sextant. And they created maps, charting coastlines and currents and hazards, building up a collective knowledge of the ocean that grew with each voyage. The age of exploration in the Sturwarth and Sirluth centuries dramatically expanded human interaction with the ocean. European ships crossed the Atlantic to the Americas, rounded Africa to reach the Indian Ocean, eventually circumnavigated the globe. These voyages were driven by economics, the search for trade routes and resources, and new lands to colonize. But they also expanded human knowledge of the ocean, revealing its true scale, its diversity, the interconnectedness of its parts. With industrialization came more intensive exploitation of ocean resources. Whaling became a major industry in the Spath and Sircuit centuries, hunting whales to near extinction for their oil. used in lamps and machinery, and their baleen, used in corsets and other products. Whaling ships ranged across the oceans, killing hundreds of thousands of whales, driving some species to the brink of extinction. Fishing also intensified. Better boats, better gear, engines instead of sails, all allowed fishermen to catch more fish, to range farther from shore, to fish deeper waters. At first, this seemed fine. The ocean was vast. Surely it could provide an endless supply of fish. But by the mid-Earth century, it was becoming clear that this wasn't true. Fish populations were declining. Some fisheries, the North Atlantic cod fishery, which had sustained communities for centuries, collapsed in the Ichenjobiers due to overfishing. Despite a moratorium on fishing, the stocks haven't recovered. Similar stories played out around the world. Bluefin tuna, once abundant, became critically endangered. Sharks, caught for their fins, declined by over 500 cheers in some populations. Bottom trawling, dragging heavy nets across the seafloor, destroyed habitat and caught enormous amounts of bycatch, non-target species killed in we were fishing down the food web, targeting the largest, most valuable species first, then moving to smaller, less desirable species as the big fish became scarce. We were using technology, sonar to find schools of fish, spotter planes, massive factory ships that could process thousands of tons of catch to extract fish faster than they could reproduce. And it wasn't just fishing. We were using the ocean as a dump. Sewage, industrial waste, agricultural runoff all flowed into rivers and eventually to the sea. Coastal waters became polluted, poisoned, eutrophic. Dead zones, areas where oxygen levels dropped so low that nothing could survive, appeared at the mouths of major rivers, fed by excess nutrients that caused massive algae blooms that died and decomposed, consuming oxygen in the process. We dumped oil deliberately and accidentally, tanker spills, offshore drilling accidents, even routine operations released millions of barrels of oil into the ocean. Oil coats feathers and fur, killing seabirds and marine mammals. It smothers coral reefs and seagrass beds. It persists in the environment for years, continuing to cause harm long after the initial spill. We dumped radioactive waste. Not just low-level waste, but barrels of high-level waste dropped into the deep ocean in the misguided belief that the ocean was so vast, so remote, that it could safely absorb our most dangerous poisons. Those barrels are still down there, corroding, leaking, contaminating the deep ocean with isotopes that will remain radioactive for thousands of years. And we dumped garbage, plastic, mostly billions of tons of plastic. The ocean has become a repository for our disposable culture. Plastic bags, bottles, fishing gear, microplastics from the breakdown of larger items, even microbeads from cosmetics, all end up in the ocean. Plastic doesn't biodegrade. It just breaks down into smaller and smaller pieces, persisting in the environment essentially forever. This plastic accumulates in massive gyres, areas where currents converge and trap floating debris. The Great Pacific Garbage Patch, a swirling accumulation of plastic debris twice the size of Texas, is the most famous, but it's not the only one. Every ocean has its garbage patches, vast areas where the surface is littered with plastic fragments, where seabirds and turtles and fish mistake plastic for food and starve with stomachs full of indigestible trash. And the plastic isn't just on the surface, it's throughout the water column, even in the deepest trenches. It's in the sediments, it's in the tissues of marine organisms, from plankton to whales. We're finding that plastics can carry toxic chemicals, both inherent in the plastic itself and absorbed from the water. These toxins accumulate as they move up the food chain, concentrating in top predators, including the fish we eat. We've also changed the ocean's chemistry. The carbon dioxide we've released by burning fossil fuels doesn't just warm the atmosphere. About a quarter of it dissolves into the ocean, forming carbonic acid, lowering the pH. The ocean is becoming more acidic, faster than it has in millions of years. This affects organisms that build shells and skeletons from calcium carbonate. It affects the behavior of fish, their ability to sense predators and find food. It affects entire ecosystems in ways we're still trying to understand, and we've warmed the ocean. As the atmosphere warms, so does the surface ocean. Warmer water holds less oxygen. It's more stratified, with less mixing between surface and deep. It affects the timing of plankton blooms, disrupting food webs. It drives coral bleaching, where corals expel their symbiotic algae and starve. It causes fish to migrate toward the poles, seeking cooler water, disrupting fisheries, changing ecosystems. Sea level is rising partly from thermal expansion as water warms, partly from melting ice sheets and glaciers. Low-lying coastal areas are already experiencing more frequent flooding. Island nations face existential threats. By the end of this century, sea level could rise by a meter or more, displacing hundreds of millions of people, inundating cities, drowning coastal wetlands that serve as nurseries for fish and buffers against storms. The ocean has absorbed much of the excess heat from global warming, buffering the atmosphere, protecting us from even more severe temperature increases. But there's a cost. That heat is driving changes in ocean circulation, in weather patterns, in the very stability of our climate system. And the ocean's capacity to absorb more heat, more carbon, isn't infinite. At some point, the ocean's buffering capacity could be overwhelmed. We are conducting an experiment on the only ocean we have, changing its temperature, its chemistry, its biology, faster than at almost any point in the past low-salute million years. We don't fully understand the consequences. We don't know where the tipping points are, what feedback loops we might trigger, whether the changes are reversible or not. But we do know this: the ocean is not infinite. It's not invulnerable. It can be damaged, depleted, degraded, and when we damage the ocean, we damage ourselves because we are not separate from the ocean. We depend on it for oxygen, for climate regulation, for food, for the very conditions that make our lives possible. The question isn't whether we'll affect the ocean. We already have. The question is whether we'll recognize what we're doing, whether we'll change course, whether we'll protect and restore the ocean before we cross thresholds from which there's no return. So what does the future hold for the ocean? That depends entirely on the choices we make now, today, in the next few years and decades. The ocean has remarkable resilience. Given time and protection, ecosystems can recover, populations can rebound, chemistry can stabilize. But resilience has limits. Pushed too hard, too fast, and systems can collapse into new states from which recovery is difficult or impossible. Now, let's start with what we can control most directly: fishing. We know how to manage fisheries sustainably. We have the science, the models, the understanding of population dynamics. What we often lack is the political will to set catch limits low enough to allow stocks to rebuild, to enforce those limits, to resist pressure from fishing industries that prioritize short-term profit over long-term sustainability. But where sustainable management has been implemented, it works, fish populations recover, ecosystems stabilize. Fishing communities that depend on those fish have reliable, predictable harvests instead of boom and bust cycles that end in collapse. We've seen it work in Iceland, in New Zealand, in parts of the United States. It's not a mystery. It's a matter of applying what we know and sticking with it even when it's politically difficult. Marine protected areas where fishing is restricted or prohibited are another tool. They allow ecosystems to function without human interference, serving as refuges where species can breed and grow. Fish and other mobile species spill over from protected areas into surrounding waters, supporting fisheries. These areas also serve as baselines, helping us understand what healthy ecosystems look like, how they function, what we've lost. Currently, about 500 baud of the ocean is in some form of protected area, though only a small fraction of that is fully protected from extractive activities. There are commitments to protect 500 sensors of the ocean by Arsenling Sanshur, an ambitious goal that would require rapid expansion of protected areas, particularly in the high seas, international waters. But protection only works if it's enforced. Paper parks, areas designated as protected but with no actual management or enforcement, don't accomplish much. Protection requires resources, monitoring, patrol vessels, penalties for violations. It requires political commitment and public support. It requires recognizing that short-term economic costs are worth long-term ecological and economic benefits. Pollution is another area where we can make progress. We know how to treat sewage, to reduce agricultural runoff, to clean up industrial discharge. It costs money, requires infrastructure, demands enforcement of regulations. But it's entirely within our capability. Rivers that were once so polluted they caught fire are now clean enough for swimming. Coastal waters that were dead zones have recovered when nutrient inputs were reduced. Plastic pollution is harder because it's so pervasive, so built into our economic system, but we can reduce it. We can eliminate single-use plastics, design products for recycling or biodegradation, improve waste management to prevent plastic from reaching the ocean in the first place, clean up existing plastic, though that's much harder and more expensive than preventing pollution in the first place. Some are developing technologies to remove plastic from the ocean, floating barriers that concentrate surface plastic for collection. These might help, particularly in garbage patches, but they won't solve the problem by themselves. We need to turn off the tap to stop the flow of plastic into the ocean, not just try to clean up after ourselves. Climate change is the hardest challenge because it's global, because it requires coordinated action across all nations, because it demands transforming our energy systems away from fossil fuels. But it's not impossible. Renewable energy technologies, solar, wind, batteries, are now cost competitive with fossil fuels in many places. We have the technology to decarbonize our economy. What we need is the political will to do it quickly enough. The ocean will continue to absorb heat and carbon dioxide even if we stop emitting greenhouse gases tomorrow. There's inertia in the system. Some changes are already locked in, but the degree of change, whether we face manageable disruption or catastrophic transformation, depends on how quickly we act. Adaptation is also important. Coastal communities need to prepare for sea level rise, for more intense storms, for changing fish populations. This might mean building seawalls, restoring coastal wetlands that buffer storm surge, diversifying economies away from dependence on particular fish species. It means planning for the long term, for a world that will be different from the one we grew up in. There are also more speculative ideas, forms of ocean geoengineering aimed at counteracting climate change. Some propose fertilizing the ocean with iron to stimulate phytoplankton growth, increasing carbon uptake. Others suggest increasing the ocean's alkalinity to counteract acidification and enhance carbon absorption. These approaches are controversial, potentially risky, poorly understood in terms of their full consequences, and we should be extremely cautious about deliberately manipulating ocean chemistry or biology on a large scale. The ocean is complex, interconnected, full of feedbacks we don't fully understand. What seems like a good idea in theory could have unintended consequences that make things worse. Before considering such interventions, we should focus on reducing the pollution and emissions causing the problems in the first place. But ultimately, the ocean's future depends on us recognizing its value, its importance, its vulnerability. For too long, we've treated the ocean as infinite, as a resource to be exploited, a dumping ground for our wastes. We've focused on what we could take from it rather than what we owe to it. We need a different relationship with the ocean, one based on respect, on stewardship, on recognition that we are part of the ocean story, not separate from it. The ocean shaped the conditions for our evolution. It continues to sustain us in ways we often don't acknowledge, and our future is bound to its future. If the ocean thrives, if its ecosystems are healthy and productive, if its chemistry is stable and its circulation functions properly, then we have a chance of a livable future. If the ocean degrades, if we push it past critical thresholds, if we break the systems that have sustained life for hundreds of millions of years, and our prospects are bleak indeed. The ocean has a memory. It remembers ice ages and warm periods, high oxygen and low, extinctions and radiations. It has survived massive disruptions before and will likely survive whatever we do to it. But whether it will be an ocean that can support us, that can provide the services we depend on, that can sustain the diversity of life it currently holds, that's less certain. That outcome depends on choices we're making right now. The memory of water. There's something I want you to understand as we near the end of our descent, something that's been woven through this entire journey. The ocean remembers, not in the way we remember, not with neurons and synapses and consciousness, but it records, it preserves, it carries within its depths and its chemistry and its sediments a history far longer and more detailed than any human archive. Like in the layers of sediment on the ocean floor, you can read climate history going back millions of years. Each layer represents a slice of time containing the shells of plankton that lived in the surface waters above, shells whose chemistry reflects the temperature and salinity and carbon dioxide concentration when they formed. Scientists drill cores from these sediments and analyze them, reconstructing past climates, understanding how the ocean and atmosphere have changed over vast scales. Timescales in ice cores from Greenland and Antarctica. You can measure ancient air trapped in bubbles, determining atmospheric composition hundreds of thousands of years ago. You can see the relationship between carbon dioxide and temperature, how they varied together through ice ages and warm periods. You can see that the current carbon dioxide level over seabed Arches parts per million is higher than it's been in at least Babbitt years, probably much longer. In coral skeletons, you can read annual growth bands like tree rings, each band recording the temperature and chemistry of the water in that year. Long-lived corals can provide records going back centuries, showing temperature variations, El Niño events, periods of stress. These records are being disrupted now as corals bleach and die, as the ocean warms past their tolerance limits. In the deep ocean, the water itself is a record. The deep circulation is so slow. Water that sank in the North Atlantic centuries ago is still flowing through the deep Pacific. That water carries the temperature and chemistry of the surface when it sank, a physical memory transported through the deep. Changes in that deep water reflect changes at the surface, but with a lag of hundreds of years. The ocean remembers. And right now, it's recording one of the most rapid changes in Earth history. The warming, the acidification, the loss of oxygen, all are happening at rates that, in the geological record, are associated with mass extinctions. We are living through and causing a transformation that will be visible in sediment cores millions of years from now, a distinct layer marking the Anthropocene, the age of humans. But the ocean's memory also gives us hope because it shows us that the Earth system is resilient. After past mass extinctions, life recovered, diversified, filled empty niches, evolved new forms. After the asteroid impact that killed the dinosaurs, after the worst mass extinction in Earth history at the end of the Permian, the ocean eventually it took millions of years, but it happened. The question is not whether life will persist. It will. Life is tenacious, adaptable, persistent. The question is whether we'll be part of that future, whether the ocean of the coming centuries and millennia will be one we can live with, one that sustains us and the ecosystems we depend on, and that depends on how we act now in this critical moment. The ocean is already changing. Some of those changes are inevitable, already in motion, beyond our power to stop, but we still have agency. We can still choose how severe those changes become, how much we lose, how difficult life becomes for us and for other species. We can choose to reduce emissions rapidly and dramatically, limiting warming to levels that are manageable rather than catastrophic. We can choose to stop overfishing, to let fish populations rebuild, to manage the ocean sustainably. We can choose to reduce pollution, to clean up our act, to stop treating the ocean as a waste dump. We can choose to protect large areas of the ocean, giving ecosystems space to function and recover. These choices won't be easy. They require sacrifice. In the short term, at least, they require changing how we live, how our economies function, what we value. They require looking past immediate comfort to long-term survival. They require caring about places we might never see, species we might never encounter, futures we might not live to experience. But we have the capacity to make these choices. We have the knowledge, the technology, the resources. What we need is the will, the collective decision that the ocean matters, that its future is our future, that we owe something to the living world that sustains us. The ocean has a memory, and it will remember what we choose to do or fail to do in this moment. Long after we're gone, the ocean will carry that memory in its depths, in its chemistry, in the species that survive or don't survive, and the ecosystems that persist or collapse. And we are writing a chapter in the ocean's history. The question is what story that chapter will tell. Plenty. We've descended as far as we can go, down through billions of years of history, through the formation of the first ocean, through the emergence of life and its transformation into the vast living system that fills the water today, down through the sunlit surface, through the twilight zone, into the eternal darkness of the abyss, down into the cold reality of what we're doing to the ocean and what that means for us. And here, in the deepest part of our journey, I want to leave you with something, not despair, though there are reasons for despair, not empty optimism, though there are reasons for hope, but urgency, a sense that this matters, that what happens to the ocean in the next few decades will shape the trajectory of life on Earth for millennia to come. The ocean is not separate from us. When we damage it, we damage ourselves. When we protect it, we protect ourselves. Every breath of oxygen, every bite of food, every drop of rain connects us to the ocean. We are not observers of the ocean's story. We are characters in it, and increasingly we're shaping its plot. The ocean has witnessed everything: the formation of the planet, the emergence of life, mass extinctions and recoveries, ice ages, and hothouse climates. It has endured, but what form it takes, what kind of ocean exists in the future, that depends on us. You don't have to be a marine biologist or a climate scientist to care about this. You don't have to live by the coast or have ever seen the ocean. You just have to breathe, to drink water, to care about the world we're leaving behind. The ocean connects all of us, whether we realize it or not. So what can you do? Educate yourself. Understand the issues, the science, the policy debates. Make choices as a consumer and a citizen that reduce your impact, reduce plastic use, choose sustainable seafood, support clean energy, Vote for politicians who take ocean protection and climate change seriously. Support organizations working on these issues. Speak up. Make your voice heard, but most importantly, care. Care about places you might never see. Care about species you might never encounter. Care about a future that extends beyond your own life. Because the ocean doesn't exist for us. It existed long before we evolved and will exist long after we're gone. But while we're here, while we have the power to affect its fate, we have a responsibility to do better. The ocean has a memory. It will remember this time, this moment when we could have changed course, when we could have chosen differently. What do we want that memory to be? A story of collapse and loss? Of a species that knew what it was doing but did it anyway? Or a story of recognition and response? Of a species that saw the danger, understood the stakes, and chose to act? We still have time, not much, and it's running out faster than we'd like to acknowledge. But we're not past the point of no return. The ocean is resilient. Give it a chance, protect it, stop poisoning it, stop heating it, stop taking more than it can give, and it can recover. Not back to what it was. Some changes are permanent on human timescales, but to something stable, something that can sustain life, something we can live with. The ocean is still beautiful, still full of wonders we haven't discovered, still capable of inspiring awe, of making us feel small in the best way, of reminding us that we're part of something much larger and older than ourselves. We can keep that, we can pass it on, but only if we choose to. And so this is where our journey ends, here in the deep, in the darkness, in the cold, but it's also where something begins. A recognition, maybe an understanding that the ocean isn't just scenery, isn't just resources, but a living system we're intimately connected to, that what happens to the ocean happens to us, that its future is our future. Listen, can you hear it? Not with your ears, but with something deeper. The ocean breathing slowly in its vast cycles. The currents flowing in patterns older than civilizations. The life adapting, persisting, enduring. The memory recorded in water and sediment and chemistry, witness to everything that's come before and everything that's coming. And the ocean is still here, still vast, still powerful, still essential, still mysterious, despite all we've learned, still capable of surprising us, of teaching us, of humbling us with its scale and age and complexity. We are of the ocean, the salt in our blood, the water in our cells, the rhythms of our body, all echo our origin in the sea. We came from the ocean, and we depend on it still. When we protect the ocean, we protect ourselves. When we harm the ocean, we harm ourselves. The choice is ours. The time is now. The ocean is waiting, not for our permission, not for our approval, but for our recognition that we are part of its story, that its fate and ours are bound together, that what we do matters. The deep blue memory continues. The ocean remembers, and it will remember us, for good or ill, for what we chose to do in this moment when the future hung in the balance. Ascend slowly. Let the pressure ease, watch the light gradually return, and when you surface, when you break through into the air and the sun, remember what you saw in the depths. Remember the history, the beauty, the fragility, the urgency. Remember that the ocean is not infinite, not invulnerable, not separate from you. Remember and act, because the ocean remembers and it's watching to see what we do next. Thank you for descending with me tonight. Thank you for listening. Thank you for caring. The ocean needs us to care, now more than ever. And if we care enough, if we act on that care, then maybe, just maybe, the memory the ocean carries forward will be one of a species that woke up in time, that recognized its connection to the living world, that chose to protect rather than destroy. The ocean has a memory longer than stone. Let's make sure it's a memory worth carrying into the future. plants. There's something else I want to show you before we ascend completely. Something that connects all the layers of the ocean's story, from the deep past to the uncertain future. Something that reveals the ocean not just as a physical system or an ecosystem, but as something more fundamental to the nature of life on Earth. And come with me to the coral reefs. Not the reefs that make headlines when they bleach, though we'll get to that, but the reefs as they've existed for hundreds of millions of years, the living structures that are among the most biodiverse ecosystems on the planet, the underwater cities that house perhaps a quarter of all marine species, despite occupying less than d of the ocean floor. Mirn's healthy coral reef is overwhelming in its complexity. Everywhere you look, there's life. Corals themselves, animals that look like plants or rocks, each polyp a tiny creature working in concert with millions of its clones to build structures that can grow for centuries. Within the coral tissue, live zooxanthellae, symbiotic algae that provide the coral with food through photosynthesis, receiving in return a safe place to live and access to the coral's waste products, which they use as nutrients. This symbiosis, this partnership between animal and algae, is fundamental to how coral reefs work. The algae provide up to bifided choshers of the coral's energy needs, allowing corals to grow in nutrient-poor tropical waters where other organisms struggle. Without the algae, most reef-building corals couldn't survive. And without the corals, the algae wouldn't have the stable, well-lit environment they need. But the reef is so much more than just coral and algae. In the crevices and caves of the reef structure live countless other organisms. Sponges filter water, processing vast quantities each day, concentrating nutrients. Tunicates, strange animals that look like blobs but are actually our distant relatives, filter feed in the current. Sea fans and soft corals add splashes of color, their polyps extended to catch passing plankton. Fish swarm everywhere. Parrotfish scrape algae from the coral surface, their beaks leaving bite marks on the rock-hard skeleton, their digestive systems grinding up coral skeleton and excreting it as sand. The white sand beaches of tropical islands, the sand you sink your toes into, much of that is parrotfish poop. Coral skeleton processed through a fish's gut. Benrelasses pick parasites from larger fish in cleaning stations, small areas where predator and prey observe a truce while the cleaning happens. Groupers lurk in caves, ambush predators, waiting for unwary prey. Sharks patrol the edges of the reef, apex predators maintaining the balance of the system. At night, the day shift retreats and the night shift emerges, an entirely different cast of characters adapted to life in darkness. And everywhere, constantly, there's reproduction, predation, competition, cooperation, death, and renewal. Coral spawn once a year in many species, releasing eggs and sperm in massive synchronized events that turn the water milky. Fish spawn, some in pairs, some in large aggregations. Larvae drift in the current, most dying, a few finding suitable habitat and settling to start new colonies, new populations. The reef is under constant threat, even in pristine conditions. Storms tear at the structure, waves break coral colonies, hurricanes can devastate entire reefs. But reefs are resilient. Broken pieces can regrow. Empty space is quickly colonized. The system has mechanisms to recover, to rebuild, to persist, but resilience has limits, and we're testing those limits in ways the reefs have never experienced before. Coral bleaching happens when water temperatures rise above the coral's tolerance threshold, usually just degrees Celsius above normal summer maximum. Stressed by the heat, the coral expels its symbiotic algae. Without the algae, the coral loses its color, turning white, bleached. Without the algae's food production, the coral begins to starve. If conditions return to normal quickly, the coral can recover, reacquiring algae, resuming growth. But if the heat stress continues too long, the coral dies. Mass bleaching events have become more frequent and more severe. The Great Barrier Reef, the largest reef system on Earth, visible from space, home to thousands of species, has experienced multiple mass bleaching events in recent years. In and again in subsequent years, heat stress has caused widespread bleaching and mortality. Some areas have lost 500 chose or more of their coral cover, and it's not just the Great Barrier Reef. Reefs worldwide are bleaching. The Caribbean reefs, once among the richest, have lost over 500 bashers of their coral cover since the Ichenjubai Tirishers. Pacific reefs, Indian Ocean reefs, Southeast Asian reefs, all are experiencing unprecedented stress. But temperature isn't the only threat. Ocean acidification, the result of carbon dioxide absorption, makes it harder for corals to build their calcium carbonate skeletons. They still can, but it takes more energy, slows growth, makes the skeleton more vulnerable to erosion. In a more acidic ocean, the balance shifts from reef building to reef erosion pollution. Pollution adds to the stress. Runoff from agriculture carries nutrients that fuel algae growth, algae that can outcompete and smother coral. Sediment from coastal development smothers reefs, blocking light, interfering with feeding and reproduction. Toxic chemicals, pesticides, herbicides, heavy metals all end up in coastal waters. All add stress to already stressed corals. Overfishing removes key species that maintain reef health. Parrotfish and surgeonfish graze algae, preventing it from overgrowing the coral. Remove these herbivores, and algae can dominate, preventing coral recruitment, turning reefs into algae-covered rubble. Removing predators can cause population explosions of prey species, which can then overgraze the reef or damage coral. Blend crown-of-thorns starfish, coral predators that normally occur in low numbers, can have population explosions when conditions favor them. A single outbreak can destroy large areas of reef, killing coral faster than it can regrow. Some scientists think these outbreaks are becoming more frequent due to nutrient pollution, which fuels the phytoplankton that starfish larvae feed on. The combination of all these stresses is overwhelming the reef's ability to cope. A reef might survive bleaching if it's otherwise healthy, if fish populations are intact, if water quality is good. But a reef already stressed by overfishing, pollution, and physical damage is far less resilient. When multiple stresses combine, when they happen repeatedly with insufficient time for recovery between events, reefs can cross thresholds from which recovery is very difficult. Some scientists think we might lose most coral reefs by mid-century if current trends continue. Not all corals, some species are more tolerant, some locations are more protected, but the vast, complex, biodiverse reef systems that exist today could be reduced to scattered remnants, rubble fields with occasional hardy survivors, a shadow of what they were. The loss wouldn't just be ecological. Hundreds of millions of people depend directly on coral reefs for food, for coastal protection, for livelihoods. Reefs buffer coastlines from waves and storms, reducing erosion and flooding. Reefs support fisheries that provide protein for island and coastal communities. Reefs attract tourists, generating billions of dollars in revenue. The loss of reefs would be catastrophic for these communities. But there's still hope. Some corals are more heat-tolerant than others. Some reefs are in locations where local conditions, upwelling of cooler water, favorable currents, make them more resistant to bleaching. These reefs could serve as refuges, sources of larvae to reseed damaged areas. Protecting these refuges is crucial. Coral restoration, growing corals in nurseries and transplanting them to damaged reefs. has shown promise in some locations. It's labor-intensive, expensive, and can only work on relatively small scales, but it can jumpstart recovery in areas where coral recruitment is low. Some projects are selecting for heat-tolerant individuals, trying to breed corals that can survive in warmer water. And there's also research into assisted evolution, using techniques to help corals adapt faster than natural selection alone would allow. This is controversial, raises questions about unintended consequences, about playing God with ecosystems. But some scientists argue that in the face of rapid human-caused change, we may need to actively help species adapt if we want them to survive. And ultimately, though, coral reefs can't be saved by local management alone. They need global action on climate change. They need us to stop warming the ocean, to stop acidifying it, to give them a chance to survive and recover. All the restoration, all the management in the world won't save reefs if we don't address the root cause of their decline. The reefs are the ocean cities, concentrated nodes of life in the vast blue desert of the open ocean. And like human cities, they're vulnerable to change, to disaster, to the accumulated impact of many stresses. But unlike human cities, we can't simply rebuild them if they collapse. Coral reefs take thousands of years to develop fully, and once lost, they may be gone for longer than human civilizations have existed. The ocean remembers its reefs. In limestone deposits on land, we can see ancient reefs, fossilized ecosystems that thrived hundreds of millions of years ago. These fossil reefs tell us that reef ecosystems have existed for vast spans of time, that they've persisted through mass extinctions and climate changes. But they also tell us that reefs can be destroyed, that there have been periods in Earth history when reefs disappeared for millions of years. Demblias, we are writing the next chapter of that history. Will it be a chapter of persistence, of reefs that adapted and survived, or a chapter of collapse, of vibrant ecosystems reduced to rubble? That depends on what we choose to do and how quickly we do it. There's a reason the ocean appears in our myths, our stories, our dreams, a reason why humans have always been drawn to water, why the sound of waves soothes us, why we feel something primal and profound when we stand at the edge of the sea. We came from the ocean, not just evolutionarily, though that's true, but in a more immediate sense. Each of us began our existence in water, in the amniotic fluid of our mother's womb, a private ocean that sustained us before birth. The ocean is in our blood, literally. The salt concentration in human blood plasma is similar to that of seawater, a remnant of our evolutionary past. We carry the ocean inside us, in every cell, in the fluids that transport nutrients and oxygen, in the tears that salt our cheeks, in the sweat that cools our skin. Being ancient peoples recognize this connection. Creation myths often feature water as the primordial substance from which everything emerged. In many traditions, water is sacred, purifying, life-giving. Rivers are holy. Springs are sites of worship. The ocean is both terrifying and wondrous, a source of life and death, abundance and danger. Modern science has confirmed what these traditions intuited. We are made of the ocean, the elements that make up our bodies, the carbon, nitrogen, oxygen, phosphorus, all cycled through the ocean for billions of years before becoming part of us. We are temporary arrangements of atoms that the ocean has held and released countless times. But our connection to the ocean goes deeper than chemistry. The ocean shapes our weather, our climate, the conditions that make our lives possible. The water cycle, evaporation from the ocean, condensation into clouds, precipitation as rain, collection in rivers that return to the sea. This cycle provides the fresh water we drink, the water that grows our crops, the water that sustains terrestrial ecosystems. The ocean moderates temperature extremes. Coastal climates are milder than interior climates at the same latitude because the ocean's high heat capacity means it warms and cools slowly, buffering temperature swings. Without the ocean, Earth would experience far greater temperature extremes, making much of the planet less habitable. Blands, the ocean drives our weather. Hurricanes, typhoons, monsoons all draw their energy from warm ocean water. Ocean currents transport heat around the planet, influencing which regions are warm or cold, wet or dry. Changes in ocean circulation can trigger climate shifts that affect continents far from the sea. The El Niño and La Niña, periodic changes in Pacific Ocean temperatures and currents, affect weather patterns globally. Droughts in Australia, floods in California, failed monsoons in India, all can be linked to these ocean cycles. Understanding the ocean is essential to understanding and predicting our weather and climate. But beyond these physical connections, there's something else. Something harder to quantify, but no less real. The ocean affects us psychologically, emotionally, spiritually. Studies have shown that being near water reduces stress, improves mental health, enhances creativity and well-being. There's even a term for it, blue mind, the meditative state induced by proximity to water. Maybe it's because water is essential to life, and recognizing that essentiality is hardwired into us. Maybe it's because the rhythm of waves mimics the rhythm of breathing, of heartbeats, creating a sense of calm and connection. Maybe it's because the ocean's vastness puts our problems in perspective, reminds us that we're part of something larger and older than ourselves. Whatever the reason, the ocean speaks to something deep in human nature. We are drawn to it, even those of us who live far inland. We seek it out, vacation by it, feel a sense of peace and awe in its presence. The ocean calls to us, and we answer generation after generation, century after century. This connection is not just poetic, it's practical. People who feel connected to the ocean, who understand their dependence on it, are more likely to support its protection, to change their behavior, to advocate for policies that prioritize ocean health. Conservation isn't just about science and policy. It's about emotion, about caring, about recognizing value beyond utilitarian measures. Banned indigenous coastal peoples have maintained this connection through traditional practices and knowledge passed down through generations. They've managed ocean resources sustainably for thousands of years, not through formal scientific management, but through cultural practices that embedded conservation into their way of life. Taboos on fishing certain areas or species, seasonal closures, respect for marine life as kin rather than mere resources, all these practice ecosystem health. We can learn from this, not by appropriating indigenous knowledge, but by recognizing that our disconnection from the ocean, our treatment of it as merely a resource or a dumping ground, is a modern aberration. For most of human history, people who lived by the ocean understood their dependence on it, respected it, worked to maintain it. Reconnecting with the ocean doesn't mean we all need to live on the coast or become marine biologists. It means acknowledging the ocean's role in our lives, making choices that reflect that acknowledgement, teaching our children that the ocean matters, that it's not just scenery but a living system we're part of. It means spending time by water when we can, paying attention to it, noticing its moods and rhythms, learning its stories. It means eating sustainably sourced seafood, or choosing to eat less seafood if sustainable options aren't available. It means reducing our use of single-use plastics, supporting clean energy, voting for leaders who take ocean protection seriously. These might seem like small actions in the face of such enormous problems, but collective action, millions of people making small changes, can have significant impacts. And more than that, each action reinforces our connection to the ocean reminds us why we care, builds the foundation for larger changes. Lem, the ocean, is our blue heart, pumping oxygen and nutrients around the planet, regulating climate, sustaining life. When the ocean is sick, we are sick. When the ocean thrives, we thrive. This isn't metaphor. It's literal reality. The ocean's health and our health are inseparable, and right now the ocean needs our help. Not our pity, not our guilt, but our active engagement, our care, our willingness to change, to protect, to restore. The ocean has sustained us for our entire existence as a species. Now it's our turn to sustain it. And so we've reached the surface again, emerged from the depths into light and air, but the journey doesn't end here. It can't, because every day we're writing the ocean's story, whether we realize it or not. Every choice we make, every action we take or fail to take, every policy we support or oppose, all of it ripples out, eventually reaching the ocean, changing it in ways large and small. The ocean's future is not predetermined. We're not helpless observers watching inevitable decline. We have agency. We can change course. We've done it before with other environmental challenges. The ozone hole is healing because we took action, phasing out the chemicals that caused it. Some fish stocks have recovered because we implemented sustainable management. Rivers that were declared dead have come back to life because we cleaned them up. These successes show us what's possible when we recognize a problem and commit to solving it. They also show us what's required: political will, public support, sustained effort over years and decades, willingness to prioritize long-term health over short-term profit. The ocean presents a bigger challenge than any we've faced before. It's vast, complex, interconnected with everything else. Problems like climate change and ocean acidification require global cooperation on an unprecedented scale. But the alternative, accepting degradation and collapse, accepting a diminished ocean and by extension a diminished world, that's not acceptable. We know what needs to be done. Reduce greenhouse gas emissions dramatically and quickly. Limit warming to levels that ecosystems can adapt to. Protect large areas of the ocean, allowing ecosystems to function and rebuild. Manage fisheries sustainably, taking only what can be replaced. Reduce pollution, particularly plastics and nutrients. Stop treating the ocean as a waste dump. Restore degraded habitats, coral reefs, mangroves, seagrass beds, salt marshes. None of this is easy. All of it requires changes to how we live, how our economies function, what we prioritize as a society. It requires acknowledging that short-term economic growth isn't worth long-term ecological collapse. It requires thinking beyond election cycles and quarterly earnings, planning for decades and centuries ahead. And it requires fundamentally a different relationship with the natural world. Not humans versus nature, not humans separate from nature, but humans as part of nature and on it responsible for it. The ocean doesn't exist for us. We exist because the ocean makes our existence possible. This shift in perspective, this recognition of interconnection and dependence is perhaps the most important change we need to make, because all the policies and technologies in the world won't save the ocean if we don't care about it, if we don't see ourselves as part of its story. But I think we do care. I think most people, when they understand what's at stake, when they see the beauty and complexity and importance of the ocean, they want to protect it. The challenge is translating that care into action, personal and political, sustained over time, even when it's difficult or
inconvenient. The ocean is patient. It operates on time scales that dwarf human lives, but it's not infinitely patient. We're running out of time to avoid the worst impacts of our actions. Some changes are already locked in, already unavoidable. But we can still determine how severe those changes become, whether we face
manageable disruption or catastrophic transformation. So, the choice is ours, not just for policymakers and scientists and activists, though they have crucial roles, but for all of us in how we live, what we buy, what we eat, how we vote, what we teach our children, what we value, what we're willing to sacrifice for. The ocean's future will be determined by the sum of billions of individual choices, yours and mine and everyone's. And that might seem overwhelming, might make individual action feel futile in the face of such an enormous challenge. But think of it differently. Each choice you make either moves us toward a healthier ocean or away from it. Each action either contributes to the solution or perpetuates the problem. You have power, real power, to influence the outcome. And you're not alone. Millions of people around the world are working to protect the ocean in ways large and small. Scientists studying ocean ecosystems, policymakers crafting protective legislation, activists raising awareness, educators teaching the next generation, entrepreneurs developing sustainable alternatives, indigenous communities maintaining traditional practices, everyday people making mindful choices. This is a movement, a shift in consciousness that's building momentum. More people than ever understand the ocean's importance, recognize the threats it faces, want to do something about it. That understanding, that concern, that willingness to act, it's growing. And if it grows fast enough, becomes widespread enough, translates into sufficient action, we can still protect most of what remains, still avoid the worst outcomes, still pass on to future generations an ocean that's alive and functional and beautiful. The horizon stretches before us, the line where ocean meets sky, infinite possibilities in every direction. We don't know exactly what the ocean of Arsène Ibite or Arsène Arbeck will look like. Too many variables, too many uncertainties, too many choices yet to be made. But we know the trajectory we're on, and we know it leads somewhere we don't want to go. So we can change trajectory, we can choose a different path. We can decide that the ocean matters enough to fight for, to sacrifice for, to reimagine our civilization around. It's not too late, but we're approaching the point where it might be. That urgency should motivate us, not paralyze us. We have work to do. Let's get started. The deep blue memory continues. The ocean remembers, and it will remember us, for good or ill, for what we chose to do in this moment when the future hung in the balance. And beyond the horizon, a personal reflection. Before we close, I want to step out of the documentary voice for just a moment to speak to you directly, person to person, about why this matters to me and perhaps to you. I've spent countless hours studying the ocean, reading research, examining data, trying to understand the systems and cycles that make it work. But my connection to the ocean isn't just intellectual, it's emotional, spiritual, even if that word means anything to you. Bayamdidi. I remember the first time I saw bioluminescence, swimming at night in warm tropical water, each movement of my hand creating swirls of blue-green light, tiny organisms responding to disturbance by flashing. It felt like swimming through stars, like the boundary between ocean and sky had dissolved. I remember feeling so small, so temporary, but also so privileged to witness that moment, that magic. Palenja. I remember diving on a healthy reef, being surrounded by so much life, so much color and movement and sound. Yes, sound. Reefs are loud, they crackle and pop and hum with the activity of countless organisms. I remember thinking that this must be what paradise looks like, this abundance, this vitality, this perfect integration of thousands of species into a functioning whole. And I remember diving on a dead reef, bleached and broken, covered in algae, silent and still. I remember the grief I felt, mourning something that had taken centuries to grow, destroyed in a season. I remember the anger at ourselves, at our inability or unwillingness to stop doing what we know is harmful. These aren't just statistics to me. These aren't abstract environmental issues. This is personal. The ocean is personal, and I think it is for you too, or can be if you let it. Maybe you've never been to the ocean. Maybe you live 1,000 kilometers inland and can't imagine ever seeing it, but you're connected to it anyway. The oxygen you breathe, partly from the ocean. The weather patterns that bring rain to your crops, driven by the ocean. The climate that makes your region habitable, moderated by the ocean, or maybe you have been to the ocean. Maybe you have memories of beaches, of swimming, of watching waves, of sunsets over water. Maybe those memories are precious to you, part of your story, part of who you are. And maybe you want your children or children somewhere to have those experiences too, to know that beauty, that power, that connection. Bence, the ocean doesn't need us. It existed long before humans and will exist long after we're gone. But we need the ocean, desperately, completely. And right now, the ocean is changing in ways that should terrify anyone paying attention. We are conducting an experiment with the only ocean we have, and we don't know how it ends. But here's the thing, we still have time to influence the outcome. The future isn't written. We're writing it right now with every choice we make. And yes, the problems are enormous, overwhelming, sometimes paralyzing in their scale and complexity, but they're not unsolvable. We have the knowledge, we have the technology, we have examples of successful conservation and restoration. What we need is the collective will to act, and that starts with caring, with feeling something when you think about the ocean, about its past and its possible futures, with recognizing that this matters, that what happens to the ocean happens to us, that we have a stake in this, a responsibility, an opportunity to do better. I don't know if this documentary has changed how you think about the ocean. I hope it has. But more than that, I hope it's changed how you feel about the ocean, because we protect what we love. We sacrifice for what we care about. We fight for what we value. The ocean has a memory, and someday, perhaps centuries from now, someone might study that memory, read it in sediment cores or ice cores or computer models. They'll see this moment, this transition, this crisis, and they'll see what we chose to do about it. Lanes, what do you want them to see? What story do you want the ocean to tell about us? So, the surface, final words. We're at the surface now. The journey through deep time and deeper water is complete. But the real journey, the one that matters, is just beginning. Mandia, you're going to leave this video or put down this transcript and return to your life. Tomorrow, the ocean will seem far away again, if it doesn't already. The daily concerns will crowd back in, the immediate demands on your attention, the 1,000 small urgencies that fill our days. Blaine, but I'm asking you to remember, to carry something from this journey with you, to let it change how you see the world, even in small ways. Combendus. When you drink water, remember where it came from, the cycle that connects rain to rivers, to ocean, to clouds, and back again. When you breathe, remember that half that oxygen came from the ocean, from organisms you can't see, floating in water you might never touch. When you hear about a heat wave, or a hurricane, or unusual weather, remember the ocean's role, how it's connected to everything. And when you make choices as a consumer, as a citizen, as a person, remember the ocean. Ask whether this choice moves towards sustainability or away from it, whether it protects or degrades, whether it acknowledges our dependence on the natural world or denies it. These might seem like small things. They are small things. But small things add up. Millions of people making slightly better choices. That creates momentum.
that shifts markets, that changes what's politically possible, that builds the foundation for larger transformations, and support the people doing the hard work, the scientists studying ocean systems, the activists pushing for policy changes, the educators teaching ocean literacy, the communities protecting their local waters, the entrepreneurs developing sustainable alternatives. They need funding, they need political support, they need to know that people care about their work. Pombalia, the ocean has sustained life for billions of years. It has witnessed the rise and fall of countless species, the transformation of the planet itself. It has endured asteroid impacts and ice ages and mass extinctions, and it will endure our impact too, one way or another. Tomdi, the question is, will it endure as a living, functioning, diverse ocean that can continue to support life as we know it, or as something diminished, simplified, degraded, unable to provide the services and support that we and countless other species depend on? That's not a rhetorical question. That's a real question with a real answer that will be determined by real actions taken or not taken in the coming years and decades. The outcome is not predetermined. We have agency, we have choice, we have still barely time. The deep blue memory continues. The ocean is still here, still breathing its slow breath, still circulating its vast currents, still supporting life in forms beyond. It's still capable of surprising us, teaching us, humbling us with its age and power and beauty. We are of the ocean. We carry it in our cells, in our blood, in our breath. When we protect the ocean, we protect ourselves. When we restore the ocean, we restore ourselves. When we honor the ocean, we honor the source of all life on this blue planet. The choice is ours. The time is now. The ocean is waiting, not for our permission, not for our approval, but for our recognition that we are part of its story, that its fate and ours are bound together, that what we do matters. The mender the ocean remembers, and it's watching to see what we do next. Make it a memory worth keeping.